Well, I will begin, since everybody's here. Dear Father, we thank you for this day. I thank you for the students. Just ask you to just bless our work today, Lord. In your name I pray. Amen. All right, so I tried to give some examples of the topology last time, which were, a little bit more out there. We looked at the lower limit topology. At least we literally looked at it. We didn't really do anything with it, but we looked at it. And come on, get a hole in my bag. It's just feeding the purpose. So I hope yesterday, like last class, gave you a window into some of the more, strange ways that topological spaces can be constructed. But I thought I should maybe take a step back here and prove some, kind of, what's the word? Relatively simple topological theorem. Let's see if we can give a topological proof. So here's a problem. We'll work on it together. Let's suppose we have a function f going from x to y, and we have another function g, which let's say is going from y to z, all right, where x, y, and z are topological spaces with topologies x, tau x, ty, and tz respective. All right. I think this is a theorem that we can prove. If these are both continuous functions, then their composite ought also to be continuous. Right? Then what's the punchline here? What can we do? G composed with f or f composed with g? Yeah, I think that's the one. I think it's G, as we tell the pre-calculus students, don't get lost in the fog. Sorry, it's horrible. I've never taught pre-calculus, so I can't be held liable for that. But this is the F, that's the G, and of course it, All right, so that is continuous. So what am I assuming? I'm going to assume these are both continuous, okay? So how do you prove a function's continuous in the topological, in this, in this completely abstract topological setting? What would the proof look like? What should you start? What's our goal? Our goal is to show that the inverse image, right, of open sets in Z under G composed with F is open where? In X, right? So what we should do is we should pick an arbitrary open set. Where? Let's let V be an element of the topology on Z. Then what can we say about F inverse of V? What's the inverse image of an open set in? Oh, I'm sorry. I should be looking at what? G, right? G. My apologies. G is here. So the inverse image of an open set in Z, right? If I draw a picture, here's my Y. Here's my z. G looks like this, right? And I'm looking at some kind of, I don't know what it looks like, whatever, v. If G is continuous, then what's G inverse of v? It's open, yeah? It's open, right? Which means it's where? It's in what?
Y.
In Y, but where? I mean, it's in the topology on Y, right? It's an open set in Y, which means it's in the topology. Like it's in Y, yes, but more specifically, it's in the topology of Y, right? Because it's an open set in Y, and the inverse image of an open set with respect to a continuous map is open again. And so I can call that thing over here U equal to G inverse of V, right? And that's an element of the topology on Y, right? I don't know what that thing looks like, but I mean, I don't know, maybe it looks like this, whatever. U. And then, of course, you've got you got x over here, right? You got this function f going from x to y. Then what? F inverse of u is an element of what? The topology of x, because why? Since f is continuous. I really should say, sorry guys, I said it in words, but I should really put up here because G is continuous, right? Hence what? F inverse of G inverse of V is an element of the topology on X. What am I trying to show? I'm trying to show that the inverse image of under G composed with F, right? So my question to you is, how is G composed with F, the inverse image of V, related to F inverse of G inverse of V? They're equivalent. You think they're equal? I mean, is it the case that G composed with F inverse of V is equal to F inverse of G inverse of V? If that's true, then that's an element of the topology of X, and hooray, we're done. We've just proved the inverse image of an open set under G composed with F is open. Are they equal? Certainly if the function's invertible, they're equal, right? But how would you, I mean, if you're not sure that those are equal, how would you check that those are equal? So you're like, to show that G composed with, I mean, write down what you're saying. You're saying to show this, should check double containment for lack of other ideas. So you said let X be an element of G composed with F inverse of V. What would that mean? That would mean that G composed with F of X is an element of what? It's an element of V, right? That's the definition of inverse image, is that if we feed it to the map, it maps to the set which we're forming the inverse image of. And that would say what? This means that G of F of X is an element of V. What does that say? F of X is an element of G inverse of V. Okay. But what does that say? Yeah, X is an element of the inverse image of the inverse image of V. Well, that's one of the inclusions that we need, right? And I think actually, if I was to be less lazy, we could probably make these biconditionals, no? Maybe not, I don't know. Yeah? Do you guys find any fault with me doing this? I mean, this is the definition of that. So I think it's definitions at every step, so. Okay, good. Then check. I mean, I knew it was true, but I was a little bit ambivalent. I thought maybe there was like a subset here or something, you know, but then there was a subset there, then I would have other issues that I might not be able to deal with. So I'm glad that it ended up being equality, because then we have, with that little bit of set theory in hand, we have a proof that we have the composition of continuous functions is continuous. So remember we defined homeomorphism last time, right? So reminder, you know, if we have X and we have y, F going to Y, and if we also have F inverse going the other way, and both F and F inverse are continuous, right? With respect, I mean, I'm assuming X and Y here are topological spaces, right? And you have a bijection with a continuous bijection with continuous inverse, then X and Y are said to be homeomorphic, right? And we write X homeomorphic to Y. And F is said to be a homeomorphism, right? So now that we know that the composite of continuous functions is once more continuous, we can then easily prove that homeomorphism is an equivalence relation on topological spaces. If I have, you know, I could say that X is equivalent to Y if and only if there exists homeomorphism. And if I had three, if I had an X and a Y and a Z, right? And if I had, you know, this was F and this was G, then of course G composed with F would go from X to Z. Yes. And that would be the composite of bijections, which is a bijection. And also, since F and G are continuous, G composed with F would also be continuous. And in this context, we'd also have the inverse, that, you know, G composed with F inverse as a function would actually, honest to goodness, be F inverse composed with G inverse, right? Again, that would be continuous because we're taking the composite of continuous functions by assumption, because we're assuming that F and G are both continuous with continuous inverse. Consequently, G composed with F is also continuous with continuous inverse, G composed with F inverse. And so if I have that X is homeomorphic to Y and Y is homeomorphic to Z, then I get that X is homeomorphic to Z. Any space is homeomorphic to itself by the identity map, right? The identity map is continuous with respect to the topology. I believe that was a homework problem for you. That feels like a homework problem. Or was that back in the metric chapter? That the identity is continuous? The identity map from a topological space to itself? What's that? Right. See, that's the problem I understand, so that might be a test question, you know? I mean, I can't ask questions I don't understand, right? Like, that's not true. You can Google. That's true. I do Google sometimes. Anyway, any space is homeomorphic to itself, and of course, if F is a homeomorphism from X to Y, then F inverse is a homeomorphism from Y to X, so it's symmetric, reflexive, transitive. And so, you know, if you think about the problem of topology, one way to look at it is it's to try to decide, you know, given all possible topological spaces, how do you group them into equivalence classes of homeomorphic spaces, right? This is one of the larger problems of topology, which is, you know, a difficult and probably impossible question to answer in general. But we can answer that question for certain specific sets of data and spaces. We can give good criteria for when spaces are homeomorphic. So one of the general problems of topology is to try to find like something that characterizes the space and is characteristic of the space in such a way that that characteristic is preserved by homeomorphisms. All right, so like today we're talking about compact and connected. These are particular traits of topological space which would be preserved under homeomorphism. Compact image of a compact set would be compact. I mean, the in fact, we have an even lazier version. Forget about homeomorphism. Actually, the continuous image of compact is compact. The continuous image of connected is connected. We don't even need invertibility of the map. All right. But if you had invertibility of the map, if you had an honest to goodness homeomorphism, then you'd actually be able to say if X is a compact space, then Y is also a compact topological space. Or if X is connected, then Y is also connected. Okay, let me get to it. Before I get to that, though, I have some pesky terminology to share with you guys. And I'll try not to belabor this too much because I really don't have much to add to the book. I just want to discuss the terminology and state the major theorems, because the major theorems are deep, useful, and really mission critical when you come to the application of topology to deeper analysis problems. So they're worth mentioning, but they're probably too hard for me to prove in here. I don't think I got paid enough for this course to prove them. Sorry. I got to be careful. If I work too much outside of class, I'll be below minimum wage, right? So you got to be careful. I don't want to violate any like labor laws, you know? So, just saying. Joking. So T1 space. What's a T1 space? What's a T2 space? What's a T3 space? And what's a T4 space? All right. T1 space means that for distinct points, X and Y and X, there exists U, V, open, all right, such that X is in U and Y is not an element of U. Oh, he stated it exactly backwards of this. He said Y is in U and X is not in U, but okay, fine. T2, also known as Hausdorff, it says for distinct X and Y, there exists U, V open, such that X is in U, Y is in V, and U intersect V are empty. So there exists disjoint open sets. You can separate points with disjoint open sets. Yeah.
What's the importance of V in the T1 space?
You don't need it. I mean, there's also let's say Y is in V and X is not an element of V. I mean, but the picture may be something like this. I don't know. Here's X. Here's Y. Here's in my language, U. And then here's V. So the open set contains the point, and it doesn't contain the other point, but you may not be able to make the you may not be able to make the U and V disjoint. Hausdorff, on the other hand, almost the same picture, distinct points X and Y, but the you can make your U like here, and you can make your V like so. As you can see, they do not intersect, Hausdorff. At least there exist disjoint open sets which separate the points. T3 space, a little bit different, and also known as regular. T4 is also known as a normal space, at least in Gamelin. Excuse me, yowzers. Great, googly moogly. All right, so for X in X and closed E subset of X, all right? So given a point in a closed subset, all right? And disjoint, all right? So here, X is not, X is an element of X with the complement of X by E, all right? This is a stupid way of saying that X is not in E, I think. Right? There exist disjoint opens, excuse me. Fine, yes, there exist disjoint open sets. So you can U comma V in the topology of X. They're disjoint. And what's the deal? E is contained in U, and X is an element of V. What's normal mean? All right, closed, pair of closed, let's say E1 and E2 subset of X. I think they should be disjoint. There exist U and V open in the topology, disjoint, and E1 is in U, and E2 is in V. So let me put it into words. In a T3 space, you can find disjoint open sets which separate a closed set from a point. All right. In a T4 space, for a given pair of closed sets which are disjoint, you can find a pair of open sets themselves disjoint which contain the closed sets. Yeah. Additional conditions for T4? Oh, there's no X and Y. What am I doing? So you're telling me that there are. Just a second here. Let me investigate your suspicion. Now, he has mentioned in his qualifying statement here that sometimes other things are discussed in this litany of terminology. So let me read from here. He says X is normal if for each pair E and F of disjoint closed subsets of X, there exist disjoint open sets U and V that contain E and F. So what were you? T4 implies what? T4 implies T3.
Because maybe there are space with the normal, with normality, like normal space.
Uh-huh.
The points may not be a closed set.
It could be a T4 space where closed. Well, he would seem to disagree with you. He says T4 implies T3 implies T2 implies T1. And his main characterization of T1 is that points are closed in a T1 space. So singletons in a T1 space are closed sets, according to. But again, I'll have to. Anyway, there's also, you could see there might be like, so Dr. Sprano was mentioning, what about the 3.5? There's also a T3.5. I'm like, I vaguely remember this from my topology as well. I would assume that's something like, see, here we've assumed that the sets are disjoint. What if you drop that? Maybe that would be like 3.5. Or maybe that would be, maybe not assuming they're disjoint, maybe that would be like 3. You could tinker with this a bit. Anyway, let me get on with it. So the main theorems that I want to share with you are as follows. First of all, every metric space is normal. Metric spaces are T4. Lemma 5.2. A topological space X is normal which was, what was that, T4, right? If and only if for each closed subset E of X and each open set W containing E, there exists an open set U containing E such that the closure of U is a subset of W. The proof of this lemma 5.2 looks relatively innocuous. Proof of 5.1 looks like it would take me a half hour to really flesh out in here, and I'm not going to do it. But let me see if I can draw a picture for this. What's it saying? It's normal for each closed subset. So if E looks like this, let's say, right? And you have an open set W, right? An open set W which is surrounding E. Maybe that would look like this. I don't know, right? That would be my W. Then there's an open set U containing E. I should have made my W bigger. Right? What does it say? So there's an open set U containing E such that the closure of U is a subset of W. So that's That's a nesting. That puts U kind of like here, right? And so like U closure, more like this, right? And that has to somehow fit inside the W. Interesting. There it is, though. This lemma 5.2. I mean, that in and of itself, I don't think is what we tend to use in applications, right? But now he says, now we arrive at the first theorem of this chapter that is not a formal definition manipulative, that is not just of a formal definition manipulative nature. In other words, the proof of lemma 5.2 really just amounts to manipulating the definition of T4, right? But this one, which is Uriason's lemma, is actually used in applications for constructing what are called bump functions. More on that in a second here. Theorem 5.3. Uriason's lemma, which is really a theorem. It says if we have E and F disjoint closed subsets of a what? Of a normal topological space, then there exists continuous F from X into the unit interval 0 to 1 such that F equals to 0 on E and F equals to 1 on F. So to draw a picture of what's going on here, I don't know what X looks like. It could be whatever. And this could be E. And these points. F, right? I mean, closed sets are kind of like out there, right? They can include you could take a closed set union, a discrete spectrum of points still be closed, typical. And it's saying that there exists a function from here to here, from the, such that all of E maps to 0 and all of F maps to 1, right? And it's continuous. So we use these to construct, as he says, bump functions here. All right, the proof of this theorem uses the dyadic rational numbers. The dyadic rational number is of the form p divided by 2 to the n. I had a close encounter with dyadic rational numbers this summer when we worked out our counterexample to the Grassmann continuation. We had to use you remember that, King? I talked to you some about that. It's technical and ugly, but they're rational numbers of a particular kind that are dense and relatively easy to manipulate. Yeah, the dyadic is like prime over 2 to the n. It's the dyadic rational number. Oh, the two-adic two-adic numbers versus like, oh, in the sense of p-adic analysis? I don't know. I'm not sure if they're connected or not. It's not in my purview. You'd have to ask Dr. Smith. He is the resident expert about the p-adic stuff. The answer to your question may be fantastically easy or fantastically complicated. I'm not sure right off the top of my head. Now, this is Tietze extension theorem. Says if we have an X is a normal topological space, Y is a closed subset of X, and F is a bounded continuous real value function on Y, then there exists a bounded continuous real function H on X such that H is equal to F on Y. So we have X normal, Y subset of X closed, all right, and F, what is F? A bounded continuous real valued function on Y. So F is going from Y to the reals, bounded. F is bounded, meaning its outputs are bounded, right? He says then there exists H from where? Oh, on X to the reals, bounded, continuous. And what else? Right, yeah, H restricted to Y is equal to the given continuous bounded function F. So both of these theorems are used in applications to make very kind of surprising constructions. Like the partition of unity, I think, is an example, which is indicated on top of page 76. Actually, that's part of the proof of Uriason's lemma. Is something that, well, to me, it reminds me of the partition of unity. It's not.
What is the H bar Y?
Oh, this is H restricted to Y. So H is a function on all of X. So that's the punchline here to the theorem, is that there exists a continuous function on the whole space that restricts to the given bounded function. Right. I think of it as something like this. If I had, I don't know, maybe Y is like this, right? And my function F, I can picture it's bounded, right? So maybe F of Y is, something like this on the real line. It's saying you can extend that function off the closed cube to the whole of R3. Because, by the way, R3 is normal. Because it's, what is it? Is R3 a metric space? I mean, I'm talking about R3 with a standard metric topology, okay? So it's definitely a normal space. And so we can take this function defined on the closed cube and extend it to be on all of R3, right? Still be bounded in such a way that it restricts to the function F on that cube. It doesn't have to have the same bound, right? Maybe it takes values a little bit beyond. We can construct the function with the same bound as a stricter theorem. Oh, okay, very good, very good. That's I guess that's a little bit more surprising, isn't it? But anyway, that's this. Okay, so all right, let me move on here and talk about compactness.
Can you draw a picture for the T3?
Oh, I can try. Let's see here. It would be, I'll do it like here, okay? So we're given a point X and a closed set. My closed sets are now becoming boxes, E. And we get to construct a disjoint open sets U, something like this, and V, something like that. Sorry, I departed from my color coding. You'll forgive me. Yeah. But yeah, I mean, T4 implies T3, implies T2, implies T1. That's the order of things here. And there are examples that illustrate these are separate cases. Like the converse is not true. T1 does not imply T2, T3 does not imply T4. These are distinct types of topology. So compactness. What's the definition? What do we mean if we say a topological space is compact? What should that mean? X is a compact topological space if what? X, a topological space, is compact if every open cover of X has a finite subcover of X, of course. So what's an open cover of the topological space? So here, that is, if there exists, let's say, U alpha in the topology of X such that the union over alpha in lambda of U alpha is equal to X. Remember, I have to allow for arbitrary unions. We shouldn't assume countable unions. So that's why I'm doing this alpha and lambda, where lambda is an arbitrary index set. It could be like a real index. You could maybe need a real variable to index it, not just countable. But anyway, if it's compact, it's kind of then what that means there's a U alpha 1, U alpha 2, U alpha n for some n in the natural numbers such that, the union I equals 1 to n of U alpha I is equal to X. So in other words, for any open cover, you can select a finite subcover. This is compact. A definition of compact. Yes?
So for any set that's accompanied by I forget what he calls it, but the topology where you're only having the full set and the empty set, that would be compact.
Oh, the useless topology?
I think that's what he calls it.
Is X, so if X, fun question. If X is a set, and topology on X is equal to empty set in X, is X compact? In this case, the only open cover is, well, I guess there are two. There's the whole topology or just the set itself?
Right.
In either case.
Actually, I guess more than this, if you would say that any topology that has a finite number of elements would necessarily be compact.
So the answer is, yeah, I would agree with you. Answer, yes. Also, and you have add-on, your add-on comment, if the number of open sets is less than infinity, then that implies a certain, that implies that every open cover has to be finite. And of course, a finite cover, if the finite cover, it's its own finite subcover. There's no expectation that the finite subcover be smaller. I mean, it'd be in some sense smaller than the original one. It just has to be finite. So yeah. But remember what he said back in the, when we started the conversation about compact, is that compact is, it characterizes some kind of finiteness. And so, yeah, it makes, in some sense, that is in good agreement here. If your topology has finitely many open sets, then yeah, maybe compactness is inescapable. Yeah. Interesting. Well, I'm not sure it's interesting, but it's true. So true anyway, yes, here. Now I claimed that compactness is a topological property, which means that it's preserved under homeomorphism. So what if we had, you know, can you see why that theorem would be true? If I had a, sorry I took the time to write lemma 5.2, that was kind of worthless. I should have skipped that one. Lemma 5.2 is really not the kind of detail I was trying to get into in that section. I mean, whatever, but indeed, theorem lemma 5.2 is, yeah. So if I was getting into the details, I would have needed it. So if f goes from x to y, and if this is, you know, suppose that's a homeomorphism, then, but in fact, like I said, there's a weaker theorem than that, which is proved here. Oh, I'm sorry. I'll get back to that in a second. There's another definition I should make. Y, a subset of X. We use A. A, a subset of X, is compact if A has compact relative topology. In other words, if the subspace topology with respect to A is itself defining a compact topological space.
Are we assuming X is compact here?
No. No. So for example, R2 is not compact. But if I took a square, if I take a closed subset, you know, of R2, it's not the whole space. If I take a closed and bounded subset of R2, then I'll be able to prove that's compact. Yep.
What is relative topology?
Relative topology. So we define tau A to be equal to A intersect U such that U is open in the original topology. So the relative topology is formed by intersecting the ambient topology wherever your, you know, A is sitting. You take all the open sets in the larger space and just intersect them with your subset that defines the so-called subspace topology.
Why is it correlated?
It's also called the relative topology. Yeah. Because it's relative to A. What is open and what is not depends on your choice of A. Yeah. It's that sense, in that sense of relative. So we can talk about whether a given subset of a given space is compact in terms of the relative topology of the object. So he also has theorem 6.1. Any finite union of compact subsets of a topological space is compact. So if you, if you have, I'll come back to this. I'm sorry. That's what I wanted to get to. But if I have A1 and I have A2, right, and then A3, etc. AK, and every one of these is compact, then the union of them is compact. So if I call the entire union A, and I look at an open cover of A, what's an open cover of? I'm not going to write anything down for this. I'm going to talk at you guys. I'm not going to write anymore. What's an open cover of A look like? I mean, an open cover of A is a union of sets. It's a collection of sets whose union covers all of these different sets, right? But since every one of those is compact, I can take a finite subcollection of each one of those subcollections, possibly infinite subcollections. I can select a finite number of them that covers this one, and a finite number of those which covers this one, and this one, and this one. And so put those together, we have a finite subcover of the entire union.
So this union has to be finite.
Yeah. Yes, finite union. I don't think the infinite union of compact sets necessarily is compact. For example, if I take the union I equals 1 to infinity of, I don't know, I to I plus 1, every one of those is a closed and bounded interval of reals. Right? Certainly everything I'm unioning is compact, because I know that closed and bounded implies compact in the metric sense. And yet that union is straight up 1 to infinity, which is not bounded and therefore is not compact, because going back to the metric stuff, which is still legit here, right, in the metric context. So theorem 6.2, a closed subspace. Oh man, stupid watch. Stop it. I thought it said 540. I'm happy now. It's 510. 540 would have been like, oh man. Theorem 6.2, a closed subspace of a compact topological space is compact. Closed subspace of compact topological space is compact. The proof of this is not that bad. All right, so what is it? If we have E is a subset of X, where E is closed. So X with E removed is what? It's open, right? It's in the topology for X. The complement of a closed set is open by definition. Closed subspace of a compact topological space is compact. Anyway, all right, so what should we do? I'm going to foolishly attempt to prove it without looking at the book. See what happens. So to prove that this closed subspace E is, I'm assuming X is compact, okay? I should look at what, maybe an open cover of E, right? In the relative sense, of course. Right? So that means that this actually has what form? Yeah, A intersect V alpha, where V alpha is in the topology for X, for all alpha in the index. Set lambda. Does that help? What is what? Oh, A. A is a mistake. I was meaning to write this. There. E, yeah, E. Okay. Then what? How about this? If we look at this picture, maybe it'll help. Right? So we've got this, like, whatever. I mean, that's some kind of open cover of E, right? You have to chop out the parts that are outside into the X space, right? In other words, the union over alpha in the lambda of U alpha equals to E, right?
So we can talk about like an extension of that open cover that covers all of X, and then say that
Oh, that's right there. So blank is an open cover of X. So what's the, you got the right idea. What do we, to cover X, what do we need to adjoin to, you know?
Oh, we can adjoin the complement of E and X, right?
Uh-huh. So, I mean, X by, E, complement of X by E, right? X minus E.
Yeah.
Is that an open cover?
Yeah.
Ah, very true. So we're not quite where we need to be yet because, well, this is definitely open. This is like, not so fast, right? That's not actually open. These are not open in X. We need, but it's easy enough to see what to do, right? Because notice that V alpha unioned with that complement. This covers X, right? Just unintersect, like go back to the original intersecting open sets that formed the relative topology. Now we have an open cover of X, but X is compact, so there exists a finite subcover, right? And it follows that there must exist a finite subcover of the U alpha. I mean, we can, if there was an infinite, if we needed an infinite number of U alphas to cover, that would contradict the finiteness of the